You get it? Ahem. 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 Oh, thank you.
Yes, sir.
Ooh. Very fancy. I will begin with a word of prayer. So, dear Father, we thank you for this day. We thank you for the weekend. It's about to start. Just pray you bless this class. Help us to make the most of the time we have, Lord. In your name I pray. Amen. Oh, before I forget, attendance. Now, just to be clear, I do not take points off if you miss classes, but I have to keep a record of when you missed, so I don't get fired. All right. Well, I don't know what actually happens if I don't do it, but I don't want to find out. But just, I feel like to reduce the confusion, I don't actually take off points if you miss classes. That's on you. I mean, missing class just makes work for you, right? So that's penalty enough, right? Besides, I take away your points in all kinds of other ways already. There's no sense of adding another way, you know? Okay, so, what's that? No? So I had a couple problems. Here's one. I want to try to solve this system over Z7, Z mod 7. And so I'm going to try to use Gaussian elimination to start with, okay? So what's the augmented coefficient matrix? Now, you say minus 6, but I say I'm going to trade that minus 6 for 1. But you're right. It would be 3 minus 6, 1. Why can I trade the minus 6 for a 1? Yeah. Oh, and that 4, what could I trade it for? How about a minus 3, right? See, that's because 4 equals to minus 3, and minus 6 is equal to 1 in mod 7, because the difference of them is a multiple of 7. 7 behaves as 0 in Z mod 7. So we identify like minus 1 with 6, and we identify 4 with minus 3. Now, I like that, because now I can be pretty lazy, right? Like row 2 plus row 1, we get 3, we get 1, you get 1, you get 0, you get 2, you get 1, right? Let's see here. Next, I would like to, so this is the forward pass is pretty much done. Well, not entirely. I really want to rescale the 3 and the 2 to 1. So I need to multiply by 3 inverse and 2 inverse. What is 3 inverse? What's the multiplicative inverse of 3? And what's the multiplicative inverse of 2 in this number system? 3 times what gives me 1? Mod 7. What's that? Well, we can just start trying stuff. 3 times 2 is 6. That's not 1. 3 times 4 is 12. That's not 1. I mean, 12 is equal to 5. 3 times 5 is 15, which is 14 plus 1. 3 times 5 is 1, mod 7. So 3 inverse is in fact 5, because 3 times 5 is equal to 15, which is equal to 1 in Z7. All right. So it looks like I should multiply the first row by 5 if I want to change that 3 into a 1. How about what's the multiplicative inverse of 2? What's that? A 4, yeah. Because 2 times 4 is 8, which is equal to 1 mod 7. So to make this 2 turn into a 1, I should multiply second row by, what did we decide? Oh, 4. 4 times row 2. So what's that give me? That gives me 1, 5, 5. And down here we get 0, 1, 4. Right, one more move, and then we'll have the reduced row echelon form. Right, so I take row 1 minus 5 times row 2, and that gives me 1, 0, oh. What's that? 5, but it's row 1 minus 5 times row 2. It's 5 minus 20, which is what? Minus 15, which is what? Minus 15 plus 21 equals to, oh, you guys told me 6. 6, very good, yeah. Aha! So apparently, the solution is x equals to 6 and y equals to 4, or the solution set is what? 6 comma 4. There it is, solution set, or the solution. Now, there's another way we can solve this problem. Check this out. So I can also look at this, of course, as the matrix 3, 1, minus 3, 1 times the vector xy equals to the inhomogeneous term 1, 0, right? I can think about this as being A. I can think about this being, say, V. I can think about this being B, right? And I can multiply by the inverse matrix, right? So this tells me that A inverse AV equals to A inverse B. So as we discussed the other day, V is equal to A inverse B. But what is A inverse? Yeah, but we should write, since we're working in Z mod 7, we should say 3 times 1 plus 3 inverse. And then, yes, this is, like you said, that's A, B, C, D. Thinking of that A, B, C, D, right? So we flip the diagonals. We put 1 here, we put 3 here. We put minuses on the off diagonals, which gives me 3 down here and a minus 1 up there. What's the multiplicative inverse of 6 out front? So guys, if you don't know what I'm doing, I'm using that formula, A, B, C, D, inverse equals to, well, I'm going to write it a little bit differently. AD minus BC inverse, flip the diagonals, put minuses on the off diagonals. This is a formula for the 2 by 2 inverse, if it exists. So what's 6 inverse mod 7? No, 6 times 6 is 36, which is 35 plus 1, which is, so 6 is its own inverse. So this is actually equal to 6. 1 minus 1, 3, 3. Which is going to be 6 times something. Now, there's something I'm missing, which is what? I'll add it in red. My vector, right? B, what is B? 1, 0, right? So that just gives you the first column, which is 1, 3. And what's that equal to? That's equal to 6, 18, otherwise known as what? Six and what? 4, which in my notation is also 6 comma 4. What do you know? Same solution. So multiplication by inverse it's a pretty decent technique for 2 by 2 systems. The nice thing about multiplication by 2 by 2 inverse is it doesn't require a lot of thinking, right? It's a formula, you write it down, you multiply, you're done. Row reduction, of course, requires a certain amount of mental effort. Not that much, but some. Any questions? All right. Another, what is it? That feels like a question.
I was wondering, up there was a negative 3 in the bottom left corner.
Ah, right. What I'm doing is I'm swapping out this 4 for minus 3. Those are equal in mod 7.
Right, and then over there it's just a regular 3. Was it something else switched?
Oh, now this right here, I'm using the I'm using this formula to get that and go to there. In fact, all of this. If you understand my purple snake comment. All right. All right, just a second here. I got to find a marker I like. These markers are a little bit, All right, somewhere in here. I need to actually throw out all the ones that don't work, but I never do. So then you get the excitement of watching me sort through markers. It's very exciting, right? Okay, so here we have a system. 2 equations, how many unknowns? 4, right? So we can use row reduction on the augmented coefficient matrix to try to solve this thing. And so let's do it. What we got? We got 1, 3, 1, minus 4, 0. And the second one, we've got 0, 2. Oh. I meant to make this a 1, guys. Let me fix it. You're not allowed to do this on tests, I always tell students. It's here. This is a, I worked very hard to get my PhD, and that's one of the privileges, is I can change problems. You're not allowed. Okay, so when you get your PhD in math, then you're also allowed to change problems. That's here. So them's the rules. So 0. Or you could just make a large contribution to the university of your choice. But yeah, 0, 2, 0. So there we go. That's the augmented coefficient matrix for my fixed problem that's more interesting. So we can do row reduction, right? So first order of business, I'm going to take row 2 minus 2 times row 1. What's that give me? Let's see, 3 times 2 is what? 6. All right, so 4 minus 6 is minus 2, right? And then we got a minus 2, right? And then we're looking at 2 plus 8, otherwise known as 10. Next move, I would, since I'm trying to find the reduced row echelon form to illustrate for you guys how that goes, row 2 divided by 2. Nice move here. Actually, I should probably divide by minus 2. And that will give me the first row unaltered, 1, 3, 1, minus 4, 0. And then we get 0, 1, 1, minus 5, 0. I'll start again over here. So the next move, I would do row 1 minus 3 times row 2. What will that get me to? 1, 0. What's that, minus 2? Let's see, minus 3 times row 2 makes that to a 15. 15 plus minus 4 is 11, right? At that point, that's the reduced row echelon form. So this system, this corresponds to the system of equations what? x1 minus 2x3 plus 11x4 equals to 0, and x2 plus x3 minus 5x4 equals to 0. The standard presentation of the solution set takes the column variables as dependent on the non-column or the non-pivotal variables. Non-pivotal variables here, non-pivots, pivots. So the pivot variables are x1 and x2. The non-pivot variables are x3 and x4. So x3 and x4 will appear as parameters in the solution set. So just to clean it up one more step here, this is x1 is equal to 2x3 minus 11x4, and x2 is minus x3 plus 5x4. So what's my solution set? Let me write it down. So we got ourselves a 2x3 minus 11x4, and then minus x3 plus 5x4 comma x3, comma x4, such that x3 and x4 are where? How many think real numbers? Votes for rational numbers. Z mod 7, yes. Rational number. There, in fact, is no right answer. It's ambiguous. I mean, you could reasonably give me any field which contains the numbers I wrote down, and the arithmetic happens as I just wrote down, right? So my question's ambiguous until I state the field of consideration, was my point. And but rationals is a good math major answer. And but let's see here. If I say over the reals, then I would put R here. Then how big is the solution set? How many things are there? What's the cardinality? If you tried to number them, you'd need an awful lot of fingers, like too many, right? Now, on the other hand, if instead of over R, I said, say, over, I don't know, let's pick Z big enough that all these things are not debatable. Yeah, Z mod 11, for example. I don't have any qualms about anything I did over Z mod 11. Yep.
Did you have to go to Z mod 12?
Well, Z12,
Or you could reduce those to zeros?
well, we can think about, did I write 12 somewhere?
No, you didn't write 12, but you wrote 11, which isn't in Z mod 11.
Oh, that just makes this 0. I mean, it's okay. The point is actually for Z over any prime, as long as we work with integers, it still makes sense. We just can sometimes reduce things down. I could put Z2 there. It would still be reasonable. It's just kind of, I'd be weird to write 10 in Z2. I mean, 10 is equal to 0 in Z2, just like a million is. Z2 has 0 and 1 as distinct representatives in the field of two elements. But anyway, if I put Z11 there, then that would put a Z11 down here. And then it becomes interesting to ask the question, how many elements are there in the solution set? You just have to count. There are 2 free Z11 parameters. How many values does each parameter, and a free variable in Z11, how many values does it take? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the size of the solution set would be 121, because that's 11 squared. Okay? If I change this to Z7, there'd be 49 solutions. If I changed it to Z2, there are 4 solutions, etc. But for an infinite field, if you have a parameter in your solution set, it's infinite. What's an infinite field is a field where you have infinitely many elements. Okay, so yeah. Most often the infinite field, in fact, always the infinite fields we'll think about in here are either the rationals or the reals or the complex numbers. So, but there are things like infinite fields that have characteristic 2, like infinite extensions of Z mod 2. Those things are out there to study. All right, one more example here. Let's see here. Suppose we have let's see here. I'll go 1, 2, minus 1, minus 2. I don't know, 3, 7, 10, 9, whatever. All right. And 0, 6. This would be what? This augmented coefficient matrix would correspond to what system of equations? 4 unknowns, 2 equations, right? This one is an inhomogeneous equation because of the 6. That one was homogeneous, right? You notice the 0 both places? This is a homogeneous equation. And in fact, by the way, side comment. If you go back to this last example, this last column of zeros we wrote, did we need to write it? I mean, in some sense, no. If you understand there's a theorem that says that Gaussian elimination, row reduction, works left to right. In other words, if I take a matrix and it's got 5 columns and I calculate the reduced row echelon form of it, if I take that same matrix and just delete the last 2 columns of it, the row reduction on the first 3 is the same. In other words, I could do this. And it would still be right, ignoring everything else I wrote with 5 things. It's still the case that this goes to that, goes to that. And that is the reduced row echelon form of this. This is the structure of row reduction. It works left to right. If you already did a row reduction and you just tack on more columns, you don't have to reinvent the wheel for the columns you've already done. You could just study what the row operations do to the new columns that you added on. Yep.
Is the number of columns corresponding to the number of the columns that don't matter?
So,
In that example, there were 5 columns and we erased 2 and nothing changed.
oh yeah, I'm saying, with regards to the homogeneous equation, just erasing the last column would be enough. But I was making a deeper point, which is that it's more than just that. We can actually delete, still true. This one's not as interesting, but we could do this too. But really, the last couple of, it starts to be uninteresting. Yeah. It's not for me. All right. Oh, but with my new shirt. Yeah. Side benefit. All right. I actually got to talk about things other than this today, so let me get on with it here. Row 1 minus 2 row 2. 1 minus 1, 3. Good grief, 3, 10. 0. 0. Oh, 0. 1. Ah, cool. That was not on purpose. We got 9 minus 20 minus 11. Yeah. Sweet. It's already in row REF form. And then all I got to do is row 1 minus 3 times row 2. And I think we'll be golden. Let's see here, 0, 0, 0, 1. Oh. I guess that's 33 plus 10. 43, right? And oh, I seem to have neglected a, I don't know why, but I just like 6, yeah. So that's 6 I should think about. And I think I have neglected. So this last column's bogus, right? That's what you guys are talking about. What should I put in that last column? Somebody tell me. I will put the correction in red. What goes here and here? I'll do the easy part. 6 goes there because that's not changed. Wait a minute. What have I done? Oh, man. I did the calculation right, but I wrote it over here. So this is where the correction needs to go. I'm supposed to write what? I'm supposed to write row 2 minus 2 times row 1. So if you were confused, good. If you were not confused, you should be more critical. There's only a point in if you watch if you participate in a lecture and you're taking notes, if you're not thinking, understandably, some things you're going to write down you're not going to think about till later, right? But you should try to think about some things. All right, and I should too. Set 0, 0, 1, it's a minus 11. 1. So that 0 is there. And, oh, this just stays 6. Well, that wasn't very exciting. All right, then what happens over here? Row 1. That means minus 18, right? Am I right? All right. At that point, this is the reduced row echelon form, right? So if I was to call this, give it a names. If that's A concatenated with B, what we're looking at over here is, in fact, the reduced row echelon form of A concatenated with B. That will give me a system of equations which has the same solution set as my initial system, although I didn't even write the equations yet, did I? So, let's suppose that this is the x1 column, this is the x2 column, this is the x3 column, this is the x4 column. So my equations here are what? x1 minus x2 plus 43 x4 equals minus 18, and x3 minus 11 x4 equals to 6. So which columns are the pivot columns? Right, column 1 and column 3, these are pivots, pivot columns. The pivot columns are the ones which are the leading ones in every non-zero row. They also will be E1, E2, ... EK after we've done the row reduction. When we do the row reduction correctly, when we get to the reduced row echelon form, every pivot column will be a standard basis element, and in order, none left out, E1, E2, E3, ... EK. And the non-pivot columns, of course, are this one and that one. So this suggests that we use x2 and x4 for parameters in the solution set. In other words, we'll write x1 and x3 as dependent variables with a dependence on the independent variables x2 and x4. So another word for parameter is independent variable. You might say free parameter, just to drive the point home. It's any real number, or any whatever field I'm working over. Let's say that these are real, for the sake of discussion. Okay, so what's the solution set? So we've got x2 minus 43 x4 minus 18, comma, 11 x4 plus 6. Ooh, I can't do math. Oopsie, oopsie. What is this? This is the second one, right? So what goes in there? Yeah, x2, kind of anticlimactic, but there it is. And then x3 is 11 x4 plus 6. And then what's x4 equal to? Well, it's equal to x4. What do you know? Okay, so, and then such that x2 and x4 are real numbers. Sorry, I got kind of cramped here due to my extravagant typesetting in the previous part of the solution set. Sorry about that. Poor planning on my part, but there's the solution set. It's worth 30 seconds of my time to point out, here's a comment to you from the future. This is also equal to x2 times 1, comma 1, comma 0, comma 0, plus x4 times minus 43, comma 0, comma 11, comma 1, plus this other piece, minus 18, 0, 6, 0, such that x2 and x4 are real numbers. It's sometimes good to look at the solution set in this kind of way. We'll come back to this later. You could do a similar thing over here, right? This we could rewrite as x3 times 2 minus 1, 1, 0, plus x4 times minus 11, 5, 0, 1. This calculation will be important to us later, but I'd rather not explain what I'm doing right now. Just I want to point out you could do that. All right. So at this point, hopefully all of you have some kind of at least rudimentary understanding of Gaussian elimination, are aware of some of its properties, but now we need to dig deeper and find a way to rip apart Gaussian elimination from the inside out in order to prove some of its deeper properties. The tool for that job is what are known as elementary matrices. So elementary matrices are really, there's a lot of things I do in linear algebra that I feel like, I would have thought of that. I could have thought of that. Formula for 2 by 2 inverse. I could have derived that myself. I feel like I'm pretty sure I would have done that. But the thought of using elementary matrices to study Gaussian elimination, man, that's an idea. I'm not sure I would have ever found that. I think I would have found something way more complicated to describe it. To me, this is one of the more beautiful constructions that I'll show you this semester. It's really neat, the idea of elementary matrices. So I'm going to work it out. Let's see here. I'll start out. I think I'm going to start out with the type 2 one because it's a little bit easier. All right. So what we're going to do is we're going to study, multiplication by E, and this E is going to be equal to the identity matrix, M by M identity matrix if you want, IM, minus EII, plus C times EII. And we're going to study multiplying that on A, where A is, say, M by N. So this thing is M by M. So we want to think about what does E times A, what's that equal to? Right? So we've got, of course, we've got IM minus EII plus C times EII, all of that times A. What does this do? What's this E matrix do to A? Right? Let's figure that out. Here C is a number. C is an element of a field we're working over, whatever that is. It could be a real number, complex number, one of these Z mod 7 deals, whatever. It's a scalar, a number. Now, we have studied, and these are the matrix units. Remember those? You've had some experience with them. So part of this is easy. What's I times A? Well, that's just A, right? Then we're looking at minus EII times A, right? Plus C times EII times A. Now, let us figure out what is E. Let's just, for the sake of future discussions in here, let's figure out what happens when we multiply EIJ on a matrix on the left. What's that do for us? So you guys write it down, think about it. What is EIJ times A? What's that do? Let me rewrite that. That is actually EI, right, times EJ transpose, right, times A. Because we figured out we can build the matrix units from the product of a column-row multiplication. And it's square, so it makes sense to use E for both. What is EJ transpose times A? That's row J, right? That's the jth row of A. So what is EI times row A? What's that do? Row J. I'll tell you what it does. It gives us a matrix which puts row J of A where is this? In which position is that? Which row is this? Yeah, that's the ith row. So that's how row column multiplication works. All right, so with that in mind, special case, I equals to j, what is EII times A? Think about it. What is that? Is a matrix that's got zeros everywhere, right? Except where it's got row what? Row I of A. Where is row I? It's in the ith row, right? In this case. And then what's that next thing? Plus the same thing, right? Except we have C times row I in the ith row, right? So what does this do? This is A with what? With row I replaced with what? C times row I. Let me put it in symbols for us. What we have then is if we take A and we do the row operation, right, of C times the ith row, that gets us to E times A. So the non-scalar multiplication of a row, I can accomplish that elementary row operation with multiplication on the left by E. Is this matrix E, is this an invertible matrix? What would its inverse be? Let's call this thing, just for the sake of nomenclature and this current discussion, let's call this E sub C, right? So E sub C. It's not hard to see that E sub 1 over C times E sub C is equal to the identity matrix. Because if you think about it, what does E sub C do? It multiplies multiplies by C, the ith row, and then this divides the ith row by C. And so the e to the E1 over C undoes what EC does. So yes, the matrix is invertible, and its inverse is simply corresponding to the natural inverse to the row up. If I asked you if you wanted to undo the row operation of multiplication by 2, you all would immediately know that to undo it, what do? You divide by 2, right? So because there's that correspondence, and there's likewise an inverse matrix for E sub C, it's just E to the 1 over C. Now, I'm not sure how long it's going to take me to actually work out. Well, I'm going to try. I want to be complete in here. We also have next, if you look at E equal to the identity matrix minus EII minus EJJ, right, plus EIJ plus EJI, all right, then we can study what is E times A of that. So I think if you understood this one, you'll actually understand this one without too much trouble. So what would E times, you think about E times A, right? So you've got A minus EII A minus EJJ A minus, plus EIJ A plus EJI A. So what's the net result of this? Think of those together. What you're looking at is the matrix with the I and jth rows removed. It just subtracts off the I and jth row. So this basically gives you, row 1. And so here's a notation for deleting something. You put a hat on it. Deleted. Well, that's not what I want. I want it to be 0. I don't know. I'm not sure a good notation for this, but there's a 0. There's another 0. This is the ith. This is the jth. And the rest of the rows are there. All right. It's probably better to write it in words than to try to write this kind of notation for it anyway. But that's got all of the rows, right? Except the I and jth have been removed. Then what does this do? This puts the ith row, right, in the what? Oh, other way around, right? It puts the jth row, rather. It puts the jth row in the ith column, right? And what's this do? This puts the ith row in the jth column. And everything else is 0, right? Everything else is 0 in those last two things. You add those to this matrix, which is mostly unaltered for A, except for the I, jth row, and what happens? The net effect is to switch row I and row j, right? So perhaps we should call this E something like E row I, flippy flop row j. Or maybe I should just call it EIJ. Oh, I can't do that. I was about to say EIJ. No. I use that for something else. But I mean, I don't know. I don't talk about these too much. But we could use that as a specific notation for this particular elementary matrix. It's the elementary matrix which swaps row I and row j. In particular, if I take the matrix A and I do the IJ row swap, then that was going to be equal to this EA, right? Or to be more pedantic, E row I switch row J to A. Again, this is an invertible matrix because it's its own inverse, right? If you multiply this matrix on itself, it's clear that you get back to the identity. So, all right. I've shown you that a type 2 operation and a type 1 operation can both be implemented by left multiplication of an appropriate invertible matrix. There's one other row operation, right? And if you look in my notes, I give a similar proof that, in fact, there exists an elementary matrix for that, and it's also invertible. So all three of our elementary row operations we can write down matrices which accomplish the same thing by left multiplication. Also, how do you actually calculate these E's? How about E sub C? Right? If you look at E sub C times I, what would that be equal to? Well, I have to kind of start a different way. If we do I, and we do C times row I, right? Then that's going to be, see, this E sub C notation is not the most awesome. I mean, we could be a little bit more. There's also a row I going on here, right? So maybe a more clumsy but more descriptive notation would be EC times row I or something like that, you know? So with that slight, clarification, my notation, EC times row I times I, right? But what's that equal to? What's any matrix times identity matrix? Yeah, it's E times C times row I. So if you want to calculate the elementary matrices corresponding to a particular row operation, you merely do that row operation to the identity matrix. It will give you the elementary matrix you're interested in. I know that those are just words to you at the moment. Here, how about this? If I take 1, 1, 0, oh, I'm sorry, the 3 by 3 identity matrix, right? And we can do row 1 swap row 2. What's that do for us? We get that, right? And let's try another one. We could also do the 3 by 3 identity, and let's say 2 times row 3. How about that? What's that going to do for us? 1, 0, 0, 0, 1, 0, 0, 0, 2, right? So the matrices on the right are, in fact, elementary matrices. If you wanted, I mean, you could take as a definition for the elementary matrix the formulas that I have been writing down at the start of our discussion. But you could just as well take the definition of an elementary matrix to be, you take the identity matrix, you perform any one of the type 1, 2, or 3 row operations, the resulting matrix is an elementary matrix. The theorem I'm trying to prove for you is that left multiplication by that matrix produces the same result as that row operation. Oh, so the other thing I haven't shown you, but we should see how it works, is something like, you know, we do mostly these type 3 things, don't we? Something like row 2 minus row 1, right? What would row 2 minus row 1 look like? So we'd have what? Minus 1, 1, 0. So let's try it out. What happens when you take the matrix 0, 1, 0, 0, I'm sorry, excuse me, 1, 0, 0, 0, 0, 1, and you multiply it by the matrix A, B, C, D, E, F, G, H, I. What happens? Try it out. What do you get? I get D, I get A, I get G, I get E, I get B, I get H, I get F, I get C, I get I. Indeed, I have done what? I have permuted rows 1 and rows 2. Let me do this one down here. I'll do the third one. 1, 0, 0, minus 1, 1, 0, 0, 0, 1 times the matrix A, B, C, D, E, F, G, H, I, for lack of imagination. So what happens? You get your A, you get your B, you get your C for the top row. In the middle one, we get, what do we get? We get minus A plus D, right? We get minus B plus E. We get minus C plus F. We get, you know, GHI. So what? What does this do for us? Here's what it does. It gives us the following theorem. For a element of, say, f m by n, there exists elementary matrices E1, E2, dot, 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 EK, such that the reduced row echelon form of A is equal to what? It's equal to EK, EK minus 1, dot, 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 E2, E1, A. Where I'm suggesting we start with A, we do row operation 1, that gets us to the first reduction of A, which is equal to E1 times A. We do the second row operation, gets us to the second reduction, which would be equal to E2 times R1, right? But E2 times R1 is actually E2 times E1 times A. So that's why I switched the ordering, etc. But anyway, Gaussian elimination row reduction terminates in a finite number of steps. To each step, there corresponds an elementary matrix, and if you just sort through it, you can view every row reduction as simply multiplication on the left of your original matrix by k successive invertible elementary matrices. This is very nice. We did not have a formula for row reduction before. It's an algorithm, right? Now we have a straight up formula. I have a connection, A equals to product of elementary invertible matrices times A. That's redundant. Every elementary matrix is invertible. So it's not like there's some invertible, some uninvertible. Well, guys, have an excellent weekend. I'll see you Monday.